Polyhedral patterns are meshes that are both regular and planar. We first show explicit constructions of polyhedral patterns on paraboloids. Starting from a tessellation in the plane, this mesh can be lifted onto a rotational paraboloid. All faces remain planar. However, lifting to other paraboloids requires the pattern to deform before being lifted. Otherwise, the faces cannot be planar. Now we show a continuous deformation of this pattern onto a paraboloid, changing its Gaussian curvature from positive to negative. Note how convex faces become concave. Here we show a continuous deformation for the Quad-Octagon pattern. As described in this paper, varying strip decompositions lead to different ways of tiling paraboloids. Again, note how convex faces become concave. This shows the deformation of another pattern used in our paper. Notice how the vertices are aligned with the rulings of the parabolic cylinder. We can configure a pattern with different strip decompositions. Here we show 3 different strip decompositions of the pattern 3-4-6-4. Different strip decompositions lead to different feasible symmetries which can be observed when mapping the pattern onto a cylinder. We color code different symmetries. For example, for the yellow faces, we observe reflective symmetries with respect to a plane bisecting the face. Vertices with the same number have a symmetry relationship. Blue faces exhibit symmetries with respect to an axis through the face barycenter. For the face barycenter shown in red, vertices with the same number have a symmetry relationship. This relationship can also be encoded for vertices of neighboring faces. We illustrate how the 3 different strip decompositions lead to very different final results. We illustrate the complete pipeline using the Soumaya model. As input, we consider a triangular reference surface mesh and a coarse remeshing, often with hexes. Then we generate an initial pattern mesh using simple geometric rules. Note that the initial mesh is not planar. Here we show the initial mesh with zoom-ins into 3 regions. The regions are chosen to highlight a positive, a 0, and a negative curvature case. As a next step, the user can select what symmetries to use in the regularizer. Here we show 2 reflective symmetries with respect to an axis through a face barycenter. For example, for the blue face barycenter, the vertices labeled 1 have a symmetry relationship. On the right, we highlight the vertices labeled 5 that are symmetric with an axis through the red barycenter. Our framework can automatically optimize the planarity of the initial pattern together with the user-specified symmetries. As we can see, the planarity was achieved by the optimization. We show a zoom into the 3 regions in the final result. We now animate the steps of our optimization from the initial mesh to the final mesh. Note that the 0 curvature regions and the negative curvature regions exhibit the strongest deformation. This is a reference surface mesh for the knot examples. Here we show the initial hex remeshing. This is the initial pattern mesh after subdivision. Note that the faces are not planar as shown in this visualization. This is the final pattern mesh. The mesh has been successfully planarized. We visualize the face deformations during the optimization process. Thank you.